Okay, so let's get started today. It'll be a busy day. First thing I'm going to start with is what I didn't actually do last time because it was all tangled up. But this is my little model for Titan. As I was saying, it has these immunoglobulin domains that bind up. So if you can sort of shorten, sort of like these magnets that come together and come apart. You know, this is really a macroscopic model, so you have to think about in the microscopic world what things are going to bind and unbind. So that's going to make it a little more spring-like. This is kind of lumpy, right? But then you also have to think you're going to have very many of these working in parallel. So those two things together is going to make it more like a smooth spring. So then just, one more piece that I'll bring up over and over again is that you guys are engineers, and so have you thinking like engineers when someone says something binds, what does that really mean? If you read a textbook and you talk to those microbiologists, it means things stick together and they're stuck together. But really it means when they bind that they're connected often, but they're going to sometimes be disconnected. And that, the tightness or affinity sets the amount of time when it's connected versus disconnected. Okay, so that was just one little piece I didn't do last time. So let's go on this lecture today. We're going to do three main things. One is force velocity relationships. The second one is line filament theory. And the third one is the Huxley 57 model. So force velocity relationships. So as I was saying last time, muscle's kind of complicated. It turns on and off. There's this dependence on length. But we look for ways when we can sort of minimize things and find easier relationships to deal with. So force velocity relations or relationships is one way we do that. And so here, what we're going to have is a setup like this, where we have the muscle here, and again a stimulator. We have a force transducer here that measures the amount of force. We have some apparatus here that can measure the length. And then we have a catch here that stops this, and we have a load. So we're going to stimulate the muscle. It's going to generate force, and at some point it's going to generate enough force to pull this lever down, and now it's going to be working against a constant load, which is set here. And so you do this experiment, and what you're going to do is you're going to assume that the muscle's basically highly activated. You're going to assume that we're working on plateaus, the force-length relationship. And when you do this, you're going to find a relationship that looks like this. So here's velocity, and here's force on this axis. And you'll get a relationship like this, which is hyperbolic. And it turns out it doesn't asymptote at these axes. It asymptotes to lines either below or behind the axes. So let's just pick a couple points here. So this is V over V max. So it's normalized velocity. So this would be the maximum velocity. And at the maximum velocity, it's generating zero force or tension. So it's just sort of, if you imagine, if you try to move your arm as fast as it can, to move it the very fastest, you can't be working against a load. If you put a load on it, it moves more and more slowly till you hit that point where you can't move at all. And that actually is this point, which is where you have zero velocity. And this would be maximum force, at least in the contraction range. Now, as it turns out with muscle, you can go to negative velocities. And so here's where you're lengthening the muscle. So if I'm pushing with maximum force, now I actually push a little more. It starts going the other way, you're lengthening, and force goes up. And then at some point, something happens and the whole thing breaks down. You either damage the muscle or you're pulling apart the cross bridges. So there is a range up here where this stops working, but over a fairly good range, you can go to negative velocities. And, this is actually how we use our skeletal muscles a lot. When we say stepping down off a curb, you're actually generating force, but your muscle's lengthening, providing some resistance to lengthening. So you also have a power curve here. So if you look at where power is work over time, and you get by multiplying the other force and velocity, then you can get a power curve. It peaks out here somewhere around 40% of maximum velocity. So the important thing about this curve is it's an invariant thing. As long as the muscle is fully activated, you will get this curve. So for every velocity, you get a corresponding force. So now, last week we talked about these classical one-parameter models where we said, well, let's assume the force generator is just pure tension element and this viscosity element. And if we looked at what we would get for force versus velocity for that, you would get a straight line, shown here in red. And that's very different from what you get with real muscle, which is this hyperbolic kind of curve. And then again, there's this negative range, and the negative range would be very different if it was this kind of element. So that says, this model, which has some value, isn't good to understand the real physiology. And I should say, really, that these classical one-parameter models, they're still used. You open up papers, if you look at papers that are on artificial muscle or robotics, this kind of simple one-parameter model is actually still used. So it has value, but it just doesn't have value here to help us understand the biophysics and the underlying physiology. This next slide, I don't want you to understand, you don't need to know the details of this, so you won't be asked about this on the test to understand each of these curves. But what this is from my collaborator Peter DeToom published this a while back. And this shows basically that this force-velocity relationship is pretty invariant. So as I was saying, muscle, you turn it on and off, so you might say, well, what happens if you're at very low activation levels? Well, it's, pretty much as you stimulate it, very quickly it comes up to its maximum velocity of shortening. This is a restatement of that, and this is that length force relationship we talked about last time. This is active force here, maximum active force, and then this is passive force. This is cut out, filling in the slides from last lecture. This is showing over a wide range of sarcomere lengths, you get essentially the same maximum velocity. V0 is the maximum velocity, sometimes called unloaded shortening velocity. So this again is where you put no load on the muscle and you activate it, that's how fast it contracts. And this next trace is interesting. Here they had a slightly different experimental setup. It wasn't like hanging a weight with a load. This just had a motor that could essentially set the load on the muscle. It was a servo motor. And what was shown here was that even if you try to make the muscle shorten faster, you can't make it shorten faster than this V0, or maximum shortening velocity. When you try to make it shorten faster, the muscle will become slack and buckle. Again, sort of like that rubber band. So this is a really important property of muscle, is this unloaded shortening velocity. And sorry. So, how can we begin to understand this force-velocity relationship? So this is a picture out of the textbooks. So this is shown here. Now we look at the level of cross bridges. This will be thick filament. This will be thin filament. This is obviously just one pair. There will be many working in parallel, but just for this illustration, what it's saying is at very high loads. So this might be a load where you can't contract. This is called isometric when you're at a fixed length. So if you have enough load that you can't even shorten, this would be isometric. And here you have a lot of cross bridges which are reaching out and pulling. And so you have a lot of cross bridges pulling. Now as you decrease the load, you're going to get some shortening velocity. And here what's going to happen is cross bridges are going to cycle. They're going to detach. So you're going to have fewer attached cross bridges. And so the force here is going to be less, because at some level force is proportional to the number of cross bridges. And then at the fastest shortening velocity, when you're moving very quickly, you have a light load. So now you have even fewer attached cross bridges. So this gives you a little bit of a conceptual model, but it's not enough. There's pieces to this that are missing. But this is at least a conceptual model to get started.
Question, why do they detach? Or how do they detach?
how did they, it's like actin-myosin with the cycle, remember it attaches, head rotates, and then it's got to detach. And the reason is because it attaches, the head rotates, so it's sort of like pulling hand over hand. It has to attach, rotate, generate some amount of force, and it detaches and it does it again. Does this make sense? Maybe I wasn't very clear about it.
So you only have to detach in order to pull more.
Yeah. So basically, you sort of attach, the head rotates, as it shortens, then the amount of pull goes away. We're going to talk about this in a second. This is a great question because this leads into the part of the lecture. But yeah, that's the basic idea. Is they have to keep detaching and reattaching sort of to refresh the amount of pull they get.
And then if you have less load, do they just not reattach? Because you said that there's less attached ones for lower loads.
Yeah, so there's fewer attached ones here. So basically, they're sort of attaching, they're shortening, and they quickly detach, and then they have to reattach again. And one net effect is that you have fewer attached cross bridges at lower loads or higher shortening velocities. Now again, this was a conceptual model, so what we're going to do in the next section is actually put some math to this and make it very explicit what's going on. But these are great questions, so just one more quick slide here before we go on. So, as I was saying here, power is work over time, and you can compute that by multiplying together the force and the velocity. So you got a power curve here. So this is maybe about 1/4 of maximum velocity, and maybe a quarter to a third of maximum load. So this is showing you why you have a 10-speed bike or like the speed. Different speeds, because if you can get your muscles working here at a certain velocity, you get the most power out of them. And so change gears, keeping the force and the power. So what gets interesting is, say, out here where you have maximum force, and by the way, I'm very sorry because in these textbooks, and even I do it, force, tension, load, they keep changing, but they're the same thing. Actually, this one says stress. So I'm sorry for that, but I think you guys will figure it out. So again, this is the lengthening and shortening on this axis, and of course this is going to die again. But luckily I have another one today. Okay, so again, this is velocity, negative velocity. This is load for stress. So now you might notice out here, this is maximum force, and this is shortening velocity. This is a force-velocity relationship. And so, if I'm pushing here on this podium, nothing's happening, but boy, I'm getting tired. So I'm doing no work, but I am getting tired because I'm using ATP. My cross bridges are cycling. So what we're going to do is now, this next section, again, make this a little clearer about what's going on. But really just the point here is that you can compute a power curve and it falls somewhere midway here. Okay, sliding filament theory. So sliding filament theory is basically that thick and thin filaments slide past each other. So when this was formulated back in the 50s, basically, if you could state it, the smallest contractile unit is the sarcomere. And sarcomere is composed primarily of actin and myosin. Now we know there's many other things, but at the time it was actin and myosin. It was found that the filaments slide but don't really change length. And then the force is proportional to the degree of overlap. To be clear, actually, it's a little more complicated because it really depends on the amount of single overlap versus double overlap. I'll get to that in a second. Then for maximum sarcomere length of about 3.6, force goes to 0, and then above that you can't get any force out of it. And then, so that was sort of the end of our length, sarcomere length force curve. And then this maximum unloaded velocity is mostly independent of sarcomere length. So that means, again, over most of the range, there's this maximum shortening velocity that you'll see out of the muscle or out of the sarcomere. So again, the sarcomere is the smallest unit of muscle. So what you see at the sarcomere level very often reflects up to a full muscle level. And interesting, all the way up to whole heart level if you're talking about cardiac striated muscle. So we had this, we discussed last week. I threw this slide in again because maybe I wasn't so clear about this point. So as I was saying, as you get to this point, you've recruited all the active myosin you can. At this point, it crosses over. Now you begin to lose cross regions. So what we do is we call this region double overlap and this region single overlap. I probably didn't say that, but it's in the homework. So I think even in the homework it says it defines that. But so basically, the amount of force is proportional to the amount of single overlap. Wherever you get double overlap, you begin to lose cross regions. So this is the same slide again, and this just points out that over very much in the sarcomere range, you get this essentially maximum unloaded shortening velocity. You go to very short sarcomere range, it changes, but over most of the range that we operate at, it's fairly fixed. Now, if you think back before people knew about active myosin, they could see the sarcomere. And really, people didn't know how muscles contracted. So there was this thought that maybe, say, there was positive charges on the thick filament and negative charges on the thin filament, and there was some kind of electrostatic interaction that would pull the sarcomere together. There's also ideas about proteins maybe sort of gliming up the way that chitin sort of balls up and pulls together. There's even theories that maybe just sort of water invades this and water sort of fattens the muscle and then it gets shorter. But really, this piece of evidence that was really hard to reconcile with is this maximum velocity being independent of sarcomere length. Because you can imagine if you had, say, positive charges on one filament and negative on the other, as you change the amount of overlap, the amount of force would change. And actually, if you had full overlap, probably force would go away because you actually have the charges as close together as possible. But yet in muscle, it's very different, right? Full overlap gives you full force. So that's really, why we came up with sliding filament theory. And that takes us to the next part of the lecture, which is, this has nothing to do with muscle, of course, but the question is, what do these things have in common? Anybody want to take a guess? Power stroke, exactly. No, not power stroke. Good guess, though. This is 57 Chevy, 57 Corvette, this is a 57 Stratocaster. These were all classics, well recognized. I tried to be a little more multicultural here. If you're into jazz, this is a classic. Classic TV, classic movie. This is Bollywood. Apparently they let the classic have Bollywood in 57. So this is an interesting year. A lot of classic things came out in 1957. So the Huxley 57 model, I think, is every bit the same kind of classic. Now, who was Andrew Huxley? Andrew Huxley won the Nobel Prize for physiology and the Hodgkin-Huxley model, which you know about. But he also did this model of muscle contraction. Now, I met Sir Andrew Huxley. I was at Oxford a few years ago. You could imagine this was a very dark, kind of medieval kind of dining hall. So this picture's a little grainy. It was made with a device you've probably never seen called a Palm Pilot. So, before smartphones. And everyone had a good camera. This is when I had a very crappy camera. So, I was really happy to meet him. I found him. I said, I'm really a big fan of this model that you developed. And he was like, well, I always hated to teach that to my students because there's so much math in it. And I said, well, that's funny because I don't really mind teaching my students any math. But, so anyway, unfortunately, he died just a little while ago, but I think he really is, one of the greats. And this model you know, if you go to a conference today, Biophysical Society, and you go to muscle talks, and people are still using this like right out of the box. I mean, this is fresh today as it was in 1957, which is, you know, 60 years ago. So anyway, so when did, I remember exactly when he died. Okay, 2012. So let's go on to the derivation as well. Now, before we jump right into this, there's a couple pieces that we have to go over to lay some foundation. Some of you may have had this, some of you may not. So it should be pretty quick. So the first one is a probability density function. So just an example here. Suppose you have a hydrogen atom and you have a proton and an electron. You find some distance r where they're apart. And so as you know from physics that, you know, this distance can vary. And so we could draw a function like this, which indicates the probability of finding it at some distance. So we're going to call this W hat. And this is a probability density function. And so what it does is, in a way, specifies the probability of finding it at some distance. So in the maximum likely, it would be most likely to be somewhere about this distance, but it could be shorter. It wouldn't go all the way to 0 here. And then the options probably is going to go down as you go further away. So one way to interpret this is that if you pick two distances, say R0 and R1, then, well, it says pick R0, so the probability of finding it any distance less than R0 is if you integrate this whole area under here. You could also do the probability between R0 and R1, where you integrate over R0 to R1 of this W hat function. So it doesn't report the probability itself in a way. So the probability of finding the electron at R equals R0 is not equal to W hat R0. If you did this, you would get 0 if you integrated from R0 to R0. So really, it's the probability over some range. Now, you know, we're all smart. We've had calculus and we understand limits. So basically, you can think about it as a limit, much the way derivative is a limit. So it's a probability of finding this between two, you know, u and u plus delta u or delta u. So take that limit. So that's another way. So, you know, an important thing is for, like in this case of the electron, is that you know it's somewhere out there. So if we integrate over all possible values, which we're going to call the domain, that has to integrate out to V1. So when you know that something is, you know, with certainty that it's somewhere over this domain, then you integrate out the probability density function into V1. So in the general case, it may not always be 1, but it's always going to be in the range of 0 to 1 here. Okay, so the next one is conditional probability. So the conditional probability is shown like this, where this is the probability of event A happening given that event B is happening. So it's really, it's A given this, given that, with this bar. And so the way to define conditional probability is the probability of both A and B happening, which is this, A and B, which is a joint probability, over just the probability of B. So another way you could write this is the joint probability of A and B occurring is going to be this probability of A given B times the probability of B. So I think most of us would probably think the probability of A and B is going to be the probability of A times the probability of B. But that's only if A and B are independent events, which sometimes happens, like when you're rolling two dice. You know, what you get on one doesn't depend. But, you know, in more general terms, you think about probability of A and B being probability of A given B. times the probability B. You can also rearrange this relationship to get probability B this way. Now this is an incredibly stupid example. So what I'm probably going to do is we're going to be a little short on time. I'm not going to go through this. You can read over this and all its stupidity, but it'll make the point really that you can't just look at two things and assume the probabilities. You can just multiply them together. The one I will talk about is this, which is something that when I was in high school we were playing Dungeons and Dragons. I had this friend that usually you want to have a higher roll. So he had this thing called random rate theory, which is basically the idea of the odds of rolling 2 1s is 1 in 36. So what you want to do is you roll the die until you get a 1, and then you say, I'm going to take the next roll. And so, if we begin to think about conditional probability, it's very clear that, the odds of rolling 2 1s is 1 in 36, but once you roll the first one, then the odds of rolling the second one is 1 in 6. So there's nothing gained here, but when you're in high school, you argue about a lot of things that you don't really understand. So we spent hours arguing about whether random rate theory was true or not. So anyway, so the third one is about state variable representations and for probabilities. And this is exactly what you did in the first section. So in the first section you had channels and you realized that they chatter open and close, but you can figure out a value which gives the mean number of open channels. So we go here. So we know any given channel can only be in one of two states, closed or open. We can have rates, which is the transition rate. We're going to use F and G very often in these lectures. But if it was a simple channel here, then the probability of the channel being open is F over F plus G. In this case, if we use 1 per second, 2 per second, it would be 1/3. You guys probably could do these in your sleep now after the first part of this class. But if you know that if you say like the probability of being open is 1/3, it doesn't mean the channel is 1/3 open. It just means if you look over some time interval, it's going to be on average open 1/3 of the time. Now one can take one channel and look over a long time, and you can take a number of independent channels and look at when they're closed or open. Here if we put 0 for closed and 1 for open, if you average this, you will get some trace like this, right? You get some amount of noise. But basically, the idea is that, instead of, one way you could solve this was actually to instantiate all these channels and sort of run it and measure it, and that's something we'll talk about later. But, a much easier way to do it is you figure out this probability, which is really the limit as you have an infinite number of channels, how many will be open and how many will be closed. Okay, great. So now we're on to the actual derivation of the model. So the Huxley 57 model is really designed to understand this force-velocity relationship. It involves sliding filament theory. It's muscle, but we're only going to look at the contractile machinery only, which means right now we're not worrying about how it turns on and off. We don't have calcium regulation. We're not worried about twitches. Just assume for now the muscle is fully activated. We can assume we're in the plateau region of the length-tension relationship, so we're not worrying right now about what the overlap is. But again, it almost doesn't matter because for the most part, it's independent of the degree of overlap. So we're going to assume that there's a constant velocity, and so this is a parameter in the model. So we're going to set the velocity and we're going to compute the force. Now, the force-velocity relationship is invariant, so for every force there's a velocity. So one could have done it a different way, but in our model we're going to set velocity as a parameter and solve for force. We're going to assume that our cross-bridges always complete one full cycle, so they're going to attach and detach, and we're going to use one ATP molecule in that process. And then we're going to assume is this model, the point of reference is an A site. An A site is an actin site. So this is where myosin binds to an actin site. And basically we have an A site and a myosin can bind to it. And whatever happens at this A site, it's independent of all the other A sites and myosin pairs. Okay, so in this model, we're going to have, again, A sites. This is a binding site on actin that we're going to assume is a thick filament, and on the thick filament are cross bridges. And in the Huxley model, they were envisioned like this, where this cross bridge could attach. It was set up between these springs like this, and when it attached, it would generate a force that was proportional to how far it was pulled out of its equilibrium position. So if this was right in the center, if the two springs were centered, it would be 0, but as you pull it one way or the other, it's going to generate a force. And force is always going to be considered parallel to the thick and thin filaments, so it's really only forces in this direction. For all the diagrams that I'm going to draw, it's going to look like this, where this is going to be our cross bridge or our myosin. This is an A site on actin, and there's going to be some distance between the equilibrium position and the position of, equilibrium position of the myosin and the position of the A site. And we're only going to consider forces in this direction, although you guys are smart and you realize that if you did attach, you would have a force that was pulling together the filaments. We're not going to consider that.
All right, do you repeat in which direction the forces go first?
Sure. Say if this myosin attaches to this A site, it's going to generate a force, but it's only going to be in this direction, which is left-right. So parallel to the thick and thin filament. Now, as I was saying, obviously if this was a spring and you attached, it might generate a force which is perpendicular to these filaments, but we're not going to ignore that.
And in the first and the other?
In this one, it's sort of a little clearer, right? This spring arrangement will really only generate a force in that direction. And again, we're going to have many of these working in parallel. This is a single example of a myosin and an A site. So these are good questions. Okay?
So in that example, the A site would be pulled to the left.
So in this example, it's not connected, so there's no force. But if we did pull this over,
Came over and grabbed this.
right?
That X that you mark at the top is a change in X with its equilibrium position, so it would pull it to the left.
It would be pulling it to the left, exactly. So this is just to remind you, what they knew in the 50s when this model was developed. I mean, this was the level of resolution they had. They didn't know about myosin. They didn't know about the head structure. They didn't understand about ratcheting. They could just see that there were thick filaments and thin filaments and some kind of connection there that they called cross bridges. So, this model that Huxley came up with, well, it made as much sense as anything at the time. So just to go on here, we're going to spend a lot of time on this setup, and I'm sorry there's a lot of slides, but actually once you understand the setup, the rest of it sort of comes together. If you don't understand the setup, then it never makes any sense. So basically, again, the point of view is around an A site. This is showing two examples of A sites. When the myosin attaches, it's, for example, in this case, is at its equilibrium position, so no force is generated in either direction. In this case, when we have a positive distortion, we're going to call it extension or distortion or strain. I'm sorry that we keep picking different names for the same thing. But basically, it's how much is it pulled out of the equilibrium position. And this is positive, it's going to be pulling in that direction. Here it's negative, it's going to generate a force in the other direction. So here the force, we're going to assume these are like an ideal spring where the force, or the tension is going to be K times X in distortion, or how far it's pulled out of its equilibrium position. So in this case, T1 here is less than T3, which is 0, is less than T2, which is positive. Now, this is an important assumption, is that these A sites are going to be spread apart by a distance. This is a small l. So the distance here is small l, and then the distance between the myosin sites we're going to call small m. And m and l and m are different lengths. And there's not a simple, say, integer relationship between them. So, then, as we're going to find out, this is important. And so, one interesting thing was that at the time that Huxley made this assumption, I don't think they actually knew what these lengths were. But as we talked about in the last lecture, you look at myosin, the heads are coming off in a given direction, in a given radial direction with a pseudo region of about 43 nanometers. So this would be the relevant distance between the myosin sites. And if we look at on the actin or the A sites, this pseudo repeat is 37 nanometers. So they are slightly different, and there's no simple kind of integer relationship like 2 to 1 or 3 to 1 or 3 to 2. So these lengths are important for a couple of reasons. One is that we don't want to consider this case where we have two myosins competing for the same A site. So this case doesn't happen, this case doesn't happen. So each A site really has one myosin that's in the range or in scope that you interact with. Now in the model, velocity is a parameter. So we're going to set the velocity. And so this is classical physics, and it's really independent of your frame of reference. What I'm going to do is I tend to assume this is fixed, the thick filament, and then the thin filament is sliding one direction or another. Now you can pick something else, but that's the convention that I'm using. So what I'm going to do is, if velocity is positive, I'm going to assume the thin filament is moving this direction. If velocity is negative, I'm going to assume it's going that direction. So let's go back for a second. So this is our model so far that we've developed. So up until this point, is there anything that would make this muscle contract in one direction versus another? Right? We've got myosins that are attaching, they generate force. But is there really a reason why it might contract one direction versus another? If there was an answer. No. Everything right now is symmetric. You just have myosin attaching to actin, and it generates a force if it's out of equilibrium, but that wouldn't really set a preferred direction of contraction. So the symmetry is broken in how the myosin is assumed attached to the actin. So what this is saying is there's an attachment rate F. And so F looks like this. It grows linearly from 0 to H. So this is the distance the myosin is from the A site. So, I'm sorry, the equilibrium position of myosin to the A site. So you can kind of think of it like this. If it's at equilibrium, it's like the myosin is attached to the thin filament. As we pull it out of equilibrium, you get a force. And in this model, it assumes that myosin likes to attach out here with a pull. So the attachment rate goes up until maximum H. So it's sort of like myosin can reach out H. H is a distance. And in fact, the rate goes up as you go further out. So it likes to attach out here at H. And then when it's out here, it's got a positive distortion or a positive strain, and it's pulling. So cross bridges like to attach pulling. So what about the detachment rate? So in the positive range, there is a detachment rate here. It grows linearly. You'll see it's just a fraction of the attachment rate, but there is a non-zero detachment rate. Here in the negative range, where we have negative strains or negative distortions, you have a very high detachment rate. So the conceptual model where there's a cross breeders want to reach out here, they attach, pulling, but because of the net motion, as the thin filament moves, the amount of distortion gets smaller. At some point, it becomes zero, and at some point, it could become negative. So what was a puller, so I'm going to say which was a puller, now becomes a dragger. So instead of helping the muscle shorten, you're now actually resisting shortening. You're a dragger. So after you become a dragger, the best strategy is to have you detach very quickly. And so this is where you're asking about cycling. So cross breeders like to attach pulling. As they shorten, they want to detach. And then after they detach, they can then reattach again, and they prefer to reattach pulling. So, in the first lecture we know about cross breeders. They have heads, they ratchet. Huxley didn't know about this. This is just saying that cross breeders like to attach out here with a positive string. Okay?
Sorry, can you clarify what the y-axis is exactly? It's rate of attachment?
Yeah, so this is an attachment rate. I'm sorry, I should have labeled it. So this is an attachment rate per second. I should opt to fix this slide. But yeah, that's what it is. I'm sorry. So we're going to, again, so this is an increasing rate of attachment. And then you can see that this relative rate of detachment is very high. Also, it's a fixed level in the negative, for negative distortions. Sorry?
Which side is pulling?
So this side is pulling.
Why is the attachment rate higher for pushing?
For pushing?
Isn't pushing the other?
So this way, right. So this way you would get force in the other direction. And so what I'm saying is, so you got pullers over here and you're a dragger. So you're saying pushing, if that's the term you want to use. You don't want pushers because they're working against the contraction. So you detach quickly.
Well, this is detachment.
Yeah, G is detachment. So F is attachment, and attachment is really restricted to this range between 0 and H. The detachment in the positive range, it doesn't stop at H, it goes all the way out here to this direction. And then in the negative range, it's a fixed high value that extends that direction.
All right, so this is saying that at distance h, the rate at which it attaches is the highest.
Yeah, so the attachment rate goes
So
up.
my question is, what if there's another place where it can attach that's at like 1/2 h? Would it attach to that one first?
Right, so what happens
At a
is,
slower rate? Because this doesn't talk about the probability of which one it's going to attach to. So does it have to attach each one like linearly, like one after the other?
yeah,
Or
so,
can it skip?
so the frame of reference here is an A site, and we're going to assume really there's only one myosin in range. So that you can only,
Okay.
and so, this is saying depending on the distance between the equilibrium position of the myosin and the A site, this is the attachment
That
rate.
doesn't seem really intuitive though, that it would attach faster to something further away.
It doesn't, but again, they didn't know about heads rotating. Sort of jump ahead, I mean, if we had a modern interpretation, what happens is, as you can imagine, it would like to attach at 0, which would be preferred, but quickly the head rotates. And now, when the head rotates, it puts strain in that link. So he didn't know that level of detail, so this was sort of, well, it just likes to go out there and grab. And so, but yeah, I mean, right, intuitively you wouldn't really think that it would prefer to go out there.
Just because it's further away.
Yeah, no, absolutely. But again, if we think like, if it attached to the closest spot, but then the head rotated and it put stretch in that spring, it becomes equivalent. So, these are all the great things you think about with this model. And later when you're alone, you'll be scratching your head trying to figure out these things, as I did. But eventually it all sort of makes sense why it was set up this way. So, I think this term just restates this about, the F and the G. So you sort of went and explained it. So I'm going to jump ahead a little bit. So what we're going to do is we're going to figure out a conditional probability, which is n of x of t. And that is going to be a conditional probability which says, you know, if you're an A site and there's a myosin in some range away from you, what is the probability that that crossbridge is attached? So if you're, you know, an A site between range x to x plus delta x from the nearest myosin, what is the probability that you have an attachment? So, you know, maybe a more intuitive way for some people might be sort of what's the probability that there's a myosin out there and it's attached? So that would be a joint probability. But we're actually going to do, again, this conditional probability which says, given one thing, what's the probability of another event? So this joint probability of both there being a myosin out there and it being attached, we're going to call n hat. So the next one, not supposed to happen. That was not supposed to happen. Gotta love Microsoft. Okay, out of blue. Okay, exclude you. Cars, excellent. Okay. Rolling dice, random ray. Okay, so gets us here. Okay, so maybe we will read. Okay, so again, this nx of t is this conditional probability which says, you know, if I'm an A site and there's a myosin some distance from me, what is the probability that that myosin is attached? If you consider a joint probability, which instead of n of x of t is n hat of x of t, which says both there's a myosin out there and it's attached. Don't know what's going on. Why does it like that? I tell you what, we'll start past that slide. So you want to make that transition. See it's happier. Sorry, guys. We're going to show it like this to hopefully get past this point. So there's this n hat, which is this joint probability. And so what we do is compute that as this conditional probability n times this probability density function w hat. W hat really gives you, if you're an A site, what is the probability of finding a myosin at some distance away from you? Okay, let's try to go back. So this is W hat. And what we're going to do is we're going to assume there's an equal probability of finding a myosin any distance from you. So the point of reference is this is an A site. There's going to be an equal probability of finding a myosin any distance away between this range of L over 2 and minus L over 2. Recall there's an A site every L down the filament. So basically it's an equal probability. So why is it equal? It comes from the fact that the distance between the myosins and the distance between the A sites are slightly different. They're out of register. So if you go over a very large number of these, you're going to find them essentially at every different spacing with equal probability. Now, if they were, say, equal, it would be very clear that things would sort of line up in register, and it wouldn't be this kind of function. It would be discrete points, but because of this unequal spacing. So here's one bit of warning that in the other 14 years I've taught this, it was h hat. But h was this other variable, and people always got it confused. No matter how many times I said h and h hat are very different. So this year I bit the bullet and said, okay, h hat dies. Now we have w hat. But if you look at all the old homework, they're going to have h hat. So in all the old tests and everything else that you can find. So again, this just restates this point that w hat's going to be a constant over this range. Okay, so now we're going to solve for this. Now, this is going to be in steady state, so we're assuming we have a fixed sliding velocity. We want to compute the force. So we have this conditional probability. It's actually a function of two variables, which is this distance and also time. But we want to solve steady state, so it's the derivative with respect to time is 0. We have to apply the chain rule. This is a step which is actually skipped in a lot of textbooks. Actually how this works, they kind of jump here, but you apply the chain rule here, which is a partial dn dx times dx dt plus partial dn dt dt equals 0. You plug in dx dt as the velocity. You rearrange to get this. This is in a way it's the governing partial differential equation that you have to solve. Now, what's the partial dn dt? Well, that's the rate of attachment to an A site minus the rate of detachment. So if you're at A site, you have minusing, which can be attaching and detaching. So if you look at this, the detached fraction is actually 1 minus n. So this is the same way that you had channels opening and closing. You had to figure out the open probability, the closed probability, and one is 1 minus the other probability. So this is the attachment rate. It's the attachment rate times the detached fraction minus the detachment rate times the attached fraction. Now what we're going to do is we're going to assume we're in steady state, so dn dt is 0, so we don't really need to track the t, and we're going to get rid of it. But it is embedded in there. We're just not going to write it. So it is embedded because things are attaching and detaching at finite rates. We're just not going to write it in the rest of the equations. So now we can combine these results. This again was the governing equation, and now we can put in these rates for the n partial dn dt. And so now this is actually what we're going to solve. And we're going to solve it in 3 different regions. The first region we're going to solve it in is x less than 0. So that's this range. So here, there's no attachment rate, f of x equals 0. There's a uniformly high detachment rate, so g of x is going to be g2. It doesn't actually depend on x. It's just a constant. In this range of 0 to h, we have an attachment rate which grows from 0 to h, so it's specified here. And we have a detachment rate that grows between 0 and h, and it's specified here. Above h, we have just this detachment rate, and it grows as a function of x, which is here. So now we have I have another important thing. There's a continuity condition, which says this conditional probability on the minus side of 0 and the plus side of 0 is going to be the same, in the same way around h. So if we go back here, so at these different points here, there's going to be a continuous value. So we're going to enforce that. So now what we're going to do is we're going to start solving in different regions. And so basically this becomes solving just ordinary differential equations because we're solving steady state. The partial differential equation we can solve as an ordinary differential equation. So in this first region between, which is x less than 0, we have an attachment rate of 0, a detachment rate of G, which is G2, which is independent of x. Again, we're solving in steady state. So we end up having to solve this equation. And so I'm going to fly through this because I need to get a little further down the line by the end of this lecture. But this is just solving differential equations. If you can look, we're going to rearrange. If you solve your differential equation, it doesn't give you one solution, it gives you a family, so you end up with a constant that you have to solve for. So in 0 to h in this range, we have an attachment rate, this, we have a detachment rate, this. They're functions of distance or distortion x. Put it together, plug it in, and we go here, we do some algebra, rearrange to get the right things on the right side. And then we can come up with this solution here, which is this kind of complicated thing, but it's a function of x. There's also a constant to solve for. And then in this region 3, what we're going to do is we have the 0 attachment rate, we have this detachment rate, but we're going to, this sort of feels a little bit like cheating, but in this case we're only considering shortening. So this is a positive velocity, this is a shortening. So since no cross bridge can reach out and extend past h, we know that for x greater than h, there's no attachment. So that means nx of t equals 0. There's nothing out there greater. So we're going to start here. For x greater than h, we're going to assume that this 0 is, so, again, this is this conditional probability. And so we're going to solve using this continuity condition across this boundary of h. And then we take the solution for n at the negative side of h as being this. And we set it to 0, and now we can solve for this constant. I'm sorry that I'm whizzing through this, but this is very easy stuff. And you look at the notes and do the math, and you can figure out how we're going to use these continuity conditions. Now we use the other one around 0, and we can compute the other constant here. And then we can figure out a whole solution here for the range of x less than 0. Now Huxley made this change of variables, so velocity he used s over 2. This is the Stockholm length, and then this is a normalized velocity. This just sort of cleans things up. It doesn't change the nature of the solution. It just changes up, makes it a little neater. This phi here, or phi, is h over 2, so this is a normalized distance times these rates. Again, this is just math that we can sort of look at, and now we can get a solution in these 3 different ranges. So for x greater than h, this probability is 0. So we're saying, out greater than h, there's no attached cross bridges. Between 0 and h, there's this function that looks like this. And then for x less than 0, there's a slightly different function. We're going to look at these in a moment. Now you have to define some rates now. So he put these rates as g1 over f1 plus g1 and g2 over f1 plus g1. Pick these 2 values. So now we're going to get to discuss the results. So this is a case of isometric, so there's no sliding velocity here. And what this is showing is this n function that says, if I'm at a site and a mine is in some distance from me, what is the probability that it's attached? And what this is showing is this is the distance here normalized by h, so this is h here. And it's saying in the range from 0 to h, there's a uniformly high value of attachment. It's about 0.8. You can compute this as f over f plus g. So it's saying under isometric conditions, you've got a lot of cross bridges at your poles. High probability of attachment, and they're all polars. So now when we go up to a higher velocity, so this is about 1/4 of V max. now you get a profile that looks like this. So if you go out to the H, the most that cross bridge can reach, and what happens is it can reach out there, but the moment it attaches, the very next moment it's shorter because you have now a net motion between the thick and thin filaments. So anything that reaches out there at maximum extension would attach and quickly get pulled shorter. And so that makes zero probability at H, but then it grows. It's a swept back kind of profile. So what's going on is cross bridges attach out here, and then they get pulled to a shorter extension. And then here, what's going on in the negative range is that these are all positive, these are pullers. Now you got draggers out here. So now you have some cross bridges that's attached pulling, now they've shortened down to 0, and now they become negative, and they're dragging, but we had this high detachment rate in the negative range, so you have some, but they kind of quickly die out. Now, let's go to V equals V max. So this is the maximum shortening velocity. Now this is where you have the very fast translation between thick and thin filaments. The maximum cross bridge can attach is H, but you see that now the probability of attachment is very low. So you have cross bridges which are attaching out here, but they quickly get pulled down to shorter distortions. And now you have a lot that get this negative distortion because they're quickly getting pulled down to 0, they become negative, and they become draggers. So this is at the maximum velocity. So remember, at maximum velocity, there's 0 net force. So there's 0 net force, not because you have 0 attached cross bridges. You actually have attached cross bridges. But what you get is, in a way, a balance between these guys pulling and those guys that are dragging. So the maximum shortening velocity, that's why it's maximum. You can't go any faster because the pullers and the draggers are now balanced. So this is the profile. So these are N. This is again, the conditional probability. You're an A site, some myosin, a myosin is some distance from you. What is the probability of attachment? Now again, in the muscle you're going to have, essentially an infinite number, a very large number of these pairs of A sites. And myosins are all acting independently, but this would be, this is how we describe, in a sense, a population using this N function. Now, the next thing we want to do is we want to compute the force. So the force is slightly different than the attachment. And the reason is that the attached cross bridge pulls with this force of this, K times X. It's like a simple or an ideal spring. So if you're an attached cross bridge, the more distorted you are, the more force you generate. So to compute force, what we have to do is we have to compute something called an expected value. And so an expected value, if people haven't taken probability or haven't seen this before, an expected value in a way is sort of an average value or a weighted average. So it's saying, let's take all the values of mu here and we're going to weigh it by this probability density function. And that will give us what we call the expected value. So to generate the force, to compute the force, we need to find the expected value. And so what we're going to do is we're going to find the force of the attached cross bridges. So this is n hat times x, which is the distortion times the spring constant. So this is the force of all the attached cross bridges. This is the force of the detached cross bridges. So this is detached A sites. The detached ones don't generate force. So this is 0. This term goes away. But just to make this seem clear and consistent, if we looked at the attached and detached A sites, we could put this together, which gives you this W hat because these two drop out. And this, if you sum over 0 to infinity, does come out to be 1. So I'm telling you this because in the homework, on the test, you will get all different variations of if you integrate, say, this versus integrating this or in this. So this just sort of lays it out. So again, n hat is actually a joint probability density function. This is a probability density function. This actually is more than actually Huxley put in the paper. We just tried to make it consistent. And actually, me and David, you and I, when we put this together a long time ago. So this is going back a bit, but the n hat is actually a joint probability, conditional joint probability. So this is this n that we define, which is this conditional probability times w hat, which is the probability density function. And because these are different spacing, w hat is a constant value between minus L over 2 and L over 2. We integrate this out, we get 1. Again, I'm sorry to go so fast, but I need to get through this. So in this case, we can compute n hat is going to be n divided by L over this range of minus L over 2 to L over 2. Outside of that, we're going to call it 0. So now we can substitute this back in for our expected value to get force. We compute this. Now we're just going to make a substitution here for nx, which was described earlier. Now, for isometric force, this is when V is equal to 0. So under isometric conditions, you have essentially all of the cross bridge out. Cross bridge is pulling. So that's going to give you the maximum force. So here we're going to just make this simple. We're going to say, we know that maximum force occurs at 0 velocity. So we plug in for 0 for the velocity, we can compute this. And now we can get a normalized force, which is this expected value over the maximum. Complicated here, but the point here is that with this model, now you can match this force-velocity relationship. It has this curvilinear feature. It's hyperbolic, but again, it doesn't asymptote at the axes. It will asymptote either behind or below the axes. And so this really did a very nice job of giving us a conceptual framework to understand, why is it that a force-velocity relationship has this kind of curvilinear nature. This slide I put in, just again, as we are trying to be very sophisticated about what models tell us. This George Box was a statistician who supposedly said this, which is all models are wrong, but some models are useful. Just sort of bringing up the point that these models are never reality. And they're going to match in some ways, and they're not going to match in others. But they give us a way to really understand a very complicated behavior and to understand it both qualitatively and quantitatively. So this model from 57, I think, was really very, superb model. It was a little bit complicated, but fairly elegant. So from this, we can understand about cross-bridge cycling. Why cross-bridge is attached, how they attach out here, and how they become negatively strained. It was able to reproduce this force-velocity relationship. Now there's also a part that we didn't talk about, which is the energy usage. So if each cross bridge attaches and detaches, it uses 1 ATP. And so you can also do this. You can also compute energy usage. And in some ways it did good at that. But it's not perfect. In this model, it's very simplistic. Cross bridges attach and detach. In reality, we know that myosin attaches, the head rotates, where ATP binds, it gets hydrolyzed. So there's more biochemistry and more steps that are involved. But he didn't know them, so we know that this is at odds with reality. That the Huxley model is too simplistic in some ways. It's got a fairly restricted set of conditions, at least in this model that I presented to you. It's either isometric, which is fixed length, or isotonic, which means fixed force, or constant velocity. So when we're shortening with the constant velocity, you have a corresponding force, which is called isotonic. In this model, it's full activation. We don't consider turning on and off the muscle. So that's another restrictive thing. They say these are problems, and these are the limitations of the model. Now, there is one thing that is a problem that we could discuss, which is what happens when you have a negative velocity. So in that case, we're lengthening the muscle. So what happens when we lengthen the muscle is that cross bridges attach between 0 and h, and then they get pulled to a longer distortion, and they detach, and they cycle. And actually, if you compute the net rate of cycling of cross bridges, it goes up as you pull the muscle and you stretch it. And so this is a problem because if you think about it, if you're stretching an activated muscle, you're actually doing work on it. So in this case, you are doing the work. But according to the Huxley model, the muscle would use more ATP when you're doing work on it. And that really doesn't make energetic sense. You would think as you do work on the muscle, it would want to use less of ATP. And that's what you see in real muscle. I tell you what, since I did speed through it, we have about 3 minutes left. Let's go back and review just a couple things that I think will help you later. So, I'm not going to ever ask you to derive all those equations to get to this point. But I am going to ask you to interpret these over and over again. It's in the homework. What you see on the homework and what you see on the test are going to be almost exactly the same. I'm going to rearrange things. I'm going to give you different cases. But basically, it's going to be the same idea. So you need to understand these. So again, between 0 and h, there's this uniformly high probability of attachment. Now, it's not 1 because all the cross bridges aren't attached. So they're attaching and detaching. So even under isometric conditions, you're attaching and detaching cross bridges. So again, if I'm pushing on this podium, I'm getting tired, I'm losing ATP, but I'm not doing any net work. This is isometric. So cross bridges are cycling even under fixed length conditions. So now when we go to a positive velocity, what's going on? Well, it becomes swept back like this because, again, any cross bridge that attaches out here to positive distortion will get pulled to a shorter distortion. But there's another important feature here, which is if you have, say, a cross bridge which is attached out here at 0.5, how did it get there? There's really 2 routes. They either attached out here at a bigger distortion and it got pulled down to 0.5, or it could have attached at 0.5. So there's really a sort of a trading of 2 things. There's what's going on, attaching and detaching at any given distortion, and what's getting pulled there. Not only what gets pulled there, but what gets taken away. So it's really this kind of trading between attachments and what's moving because you have this net translation of the thick and thin filaments. So you might also notice that if you look, say, at the maximum probability of attachment, it's lower. So as cross bridges are cycling, as we were talking about, this came up earlier, you asked the question about why does the ratio go down. It's because as you begin to have this shortening velocity, they are detaching and cycling, and so the probability of attachment goes down, even under the highest fraction, the highest probability of attachment. And then if we go here, again, this is at maximum velocity. So here it becomes very swept back. Anything that attaches pulling quickly goes to a shorter distortion, it's pulling less, and then you have a lot that get pulled to these negative distortions. Now, this question is going to come up at some point, which is in the homework, you're going to see on the test, which is, do you expect if you integrate this area and that area that they're going to be equal? Because at some level you got this you got pullers, and you got draggers, and they're in this equilibrium. So should these be equal areas? And the answer is no. You would think that, it would make a lot of sense, but the point that you have to remember is that a cross-bridge attached with zero distortion doesn't pull, right? The amount of pull is how distorted it is. So these guys, say out here, there's not as many attached ones, so they pull a lot. When you get to zero, there's a higher probability of attachment, but it doesn't pull. So you have to also, so you take this, which is the probability of attachment, but then you have to weight it by how much. So that's where this expected value comes in and in the subsequent slides. So this is a good place to stop.
So you weight it, then it would be zero.
Right. So
So it's not just the area, you're saying you still weight each point.
you have to weight each point. So the weighting goes up this
So
direction.
you're not pulling. Like you have to pull it.
So, right. So if we weighted it properly, then the two areas are equal.